Welcome back, everyone. So, in our last deep dive, we really got tangled up in the paradoxes at the very heart of quantum mechanics. Well, today, we're taking the next big step. We're going to explore what is maybe the most profound and, honestly, the most elegant solution ever proposed. We're just going to follow the math and see where it takes us. All right, let's just jump right in with a single question that really changes everything. The standard story, the one we all learn, is that when we look at a quantum system, its fuzzy cloud of possibilities, it just snaps into one single reality. But what if that's wrong? What if the collapse never actually happens? What if it's just a convenient fiction we invented because the alternative was too much to handle? To really get why we'd even think that, you have to understand the big problem with the traditional way of thinking, what's known as the Copenhagen interpretation. See, it's got this fundamental conflict. It basically says reality has to play by two completely different sets of rules. And here is that contradiction, laid bare. When nobody's looking, a quantum system just evolves. It does so beautifully, predictably, following the smooth mathematics of the Schrödinger equation. Everything's deterministic. But then, the instant we measure it, bam, a totally different rule kicks in. The wave function supposedly just collapses violently into one random outcome. Think about it. It's like saying your car obeys the laws of traffic, right up until you look at the speedometer, and then it instantly teleports to a random spot on the highway. It just doesn't make logical sense. You know, this two-rule problem drove one of the giants of the theory, Erwin Schrödinger, absolutely nuts. His whole famous cat-in-a-box idea, it wasn't him trying to say, wow, look how weird quantum physics is. No, it was the opposite. He was trying to show how utterly absurd the idea of collapse was, by scaling it up to something you couldn't ignore, a cat that is somehow both alive and dead. He was practically shouting, look how ridiculous our theory becomes. And it was exactly that frustration that set the stage for a grad student back in the 1950s, a guy named Hugh Everett III, to come along with a solution that was just breathtaking in its simplicity. He basically asked, what if we just, delete the second rule? See, Everett's idea wasn't about making things more complicated. It was about making them radically simpler. He said, let's just trust our own math. What if there's only one rule for everything, the Schrödinger equation, and it's always on, for everything, whether we're looking or not? What if the act of measurement isn't some strange magical process, but just another physical interaction, same as any other? And that simple idea leads you to this, the universal wave function. The concept here is that everything, and I mean everything, every single particle, every star, you, me, the screen you're watching this on, is all just part of one single gigantic quantum state. This whole state, the entire universe, just evolves perfectly and deterministically forever. No collapse, no exceptions, just pure, clean math. Okay, so what does this mean for Schrödinger's poor cat? I mean, if the wave function never collapses, why is it that when we open the box, we only ever see one outcome, a live cat or a dead cat, never both, right? Well, the many worlds interpretation gives us a real physical reason for this, and the key is a process called decoherence. Let's just walk through this, because this is the magic trick. First, that radioactive atom is in a superposition. It's both decayed and not decayed. Okay, that state gets entangled with the detector. But here's the crucial part the old theory just kind of ignored. That detector isn't floating in a perfect void. It's constantly bumping into air molecules, getting hit by photons. The whole environment gets entangled with it. And in doing so, it makes a record of the detector's state. That incredibly fast, messy entanglement is decoherence. And it's what splits the universal wave function into separate, non-interacting branches or worlds. So when you open the box, you just get entangled too, finding yourself on one of those branches. And that's the whole ballgame right there. Measurement stops being this mysterious, almost philosophical event. It's just a physical process. It's decoherence. It's what happens when a small quantum systems business gets broadcast to its entire neighborhood. The collapse we thought we were seeing was just us, from our own point of view, landing in one of these new separate branches of reality. Now I know. I can hear you thinking it. This sounds absolutely wild. Creating a whole new universes every time an atom decays, it sounds extravagant. And that raises some really good, really important questions. So let's face the biggest objections head on. Okay, first up, the big one. What about the conservation of energy? I mean, this is like physics 101. You can't just create energy out of nothing. So if you're spinning up whole new worlds, where is all that stuff coming from? Well, the answer, as physicist Sean Carroll puts it so well, is that you're not actually creating anything new. It's much more like a subdivision. So picture the total universal wave function as having a fixed, constant amount of energy. When it branches, that energy just gets divided up among the new branches. From a bird's eye view of the whole multiverse, mathematically nothing has changed. The total energy is 100% conserved.
All right, so energy is safe. But that just leads to the next mind-boggling question. How many of these worlds are we talking about? And how often is this branching actually happening?
So the honest answer is a lot, and it's happening constantly. Every single time a quantum superposition interacts with its environment, a branch happens. Just to give you a sense of scale, inside your own body right now, there are about 5,000 radioactive decays happening every single second. Each one of those is a quantum event. Each one could be splitting your reality into thousands of different futures. The number is, frankly, ginormous. It's just staggeringly huge. And that enormous number naturally leads to a classic sci-fi idea, right? If there are that many worlds, does it mean that anything you can imagine is happening somewhere? Is there a world where you're a king? Or a world where, I don't know, gravity works backwards? No, absolutely not. And this is so important to get right. Many worlds is not a free-for-all. In fact, it's the total opposite. It says that reality is only and strictly governed by the math of the Schrödinger equation. If an event has a zero probability in that equation, say an electron spontaneously turning into a proton, it's not going to happen. Not here, not in any branch, ever. The laws of physics are still the laws of physics. So when you put all of these pieces together, what you get is this incredible shift in perspective. You get the many worlds interpretation. And it's not a multiverse from a comic book. It's a multiverse that falls directly out of the equations we already have. Let's just put the two views right next to each other. On one hand, you have the old Copenhagen view, a reality that's fundamentally random, where we, the observers, have this weird magical power to force reality to make a choice. The wave function is just a calculator. But in the many worlds view, reality is totally deterministic. The wave function is the reality. And we aren't special. We're just along for the ride, part of the system, getting carried down one of its countless branches.
And this, for me, is the biggest takeaway.
In the many worlds picture, the physics itself isn't weird at all. The Schrödinger equation is smooth, it's deterministic, it's beautiful. All the quantum weirdness we talk about, the randomness, the uncertainty, the spooky action, it's all just an illusion. It's a side effect of our limited point of view, of the fact that we are trapped on a single branch, unable to see the whole magnificent structure. So I'll leave you with this to chew on. What if this reality, everything you see and touch and experience, isn't the whole picture? What if it's just one tiny sliver of a much larger, much grander, and ultimately much simpler mathematical truth that we call the universal wave function? This has been our second deep dive into these big ideas. If your brain isn't completely melted and you want to keep pushing the boundaries, make sure to check out the rest of our Cosmic Mysteries and Physics Paradoxes playlist. We'll see you over there.